7.7 Mole Relationships in Chemical Equations. Now, in this section, our learning goal is to use a mole-to-mole factor from a balanced chemical equation to calculate the number of moles of another substance in the reaction. So, I know that might make you think, oh, well, this one's not important. It's actually just the opposite. This is the key right here. This section is the key to tying in what we learned earlier in Chapter 7, applying the reason of having balanced equations to being able to get to the next thing that we're going to learn about, which is in our next section. So this is a key here to get from what we learned earlier to our next section. So please, hopefully, help yourself try to understand this. If you don't understand this section by the time we're done with this section, please look at more links or send me an email and say, hey, I don't understand this concept. Send me a message. So first of all, the law of conservation of mass, which we've alluded to before, but we've never said the law of conservation of mass, okay? But the law of conservation of mass, which applies, indicates that in an ordinary chemical reaction, that means a non-nuclear chemical reaction, matter can neither be created nor destroyed, that no change in total mass occurs, and that the mass of the products is equal to the mass of the reactants. So, not that you need to memorize that, you don't. But we're going to use this concept and we're going to figure out use our balanced equations to be able to calculate how much products we're going to get. And that's what we're going to get to in the next section. So first of all, let's look at this formula here. We have silver plus sulfur gives us silver sulfide. Now, we balanced the equation at one point in time. We put a 2 in front of it so that it's balanced. And the reason why we put a 2 in front of it so that it's balanced is because matter is neither created nor destroyed. So let's see what we're meaning here. So we have the mass of our reactants. So the mass of our silver, the mass of our sulfur, and the mass of the product. So because we had 2 silvers, 2 moles of silver, 1 mole of sulfur, and 1 mole of silver sulfide, you will notice that the masses, so here's our weighing devices, that when you add the masses up, that the mass of the reactants equals the mass of the products. So in table 7.6, we have our equation. We can look at it in different ways. That this 2 is going to tell us, okay, we have 2 of these units. The way that we really think of it and use it in our measuring is moles. So we have 2 moles of silver to 1 mole of sulfur. And it gives us 1 mole of silver sulfide. And then if you plug the mass in for our silver, the mass of 1 mole of silver is 107.9. If you look on the periodic table, you'll see that. So 2 times that is 247.9. The mass of 1 mole of sulfur is 32.07. And then the mass of 1 mole of silver sulfide is 247.9. So you'll notice that when you add up the reactants, they equal the products. Now, consider the following equation. Here we have another equation. 2Fe plus 3S gives us Fe2S3. So, the way that it's really read, instead of the way I did it, is 2 moles of iron plus 3 moles of sulfur is going to give us 1 mole of iron 3 sulfide. And that's an important concept there, that this is a mole to mole ratio. 2 moles to 3 moles will produce 1 mole of our iron 3 sulfide. Our mole to mole factor is a ratio of the moles for any 2 substances in that particular equation. So if we need a ratio between iron and sulfur, it is 2 moles of iron to 3 moles of sulfur. Or we could have inverted it, and we could have said 3 moles of sulfur to 2 moles of iron. And you go, well, which one do you want? Well, it depends on what they're asking for in the equation. And then you're going to, of course, cancel out, and we're going to set it up so that the labels cancel out. But if we had needed a relationship between iron and iron 3 sulfide, well, the number in front of the iron is 2 moles of iron to 1 mole of iron 3 sulfide, or we could have inverted it and put the 1 mole of iron 3 sulfide on top and the 2 moles of iron on the bottom. Or if we needed the relationship between our sulfur and the iron 3 sulfide, the relationship between the sulfur and the iron 3 sulfide is 3 moles of sulfur to 1 mole of iron 3 sulfide, or we could have written it the other way around, 1 mole of iron 3 sulfide to 3 moles of sulfur. Now, let's see if we can figure this one out. So here's our first set of problems. So consider the following equation. Here's our equation of 3H2 plus N2 gives us 2NH3. So the mole-to-mole factor for hydrogen and nitrogen is, okay, so let's see. It's 3 moles of hydrogen to 1 mole of nitrogen. Oh, right here, number 2. 3 moles of hydrogen to 1 mole of nitrogen. Now, B. A mole-to-mole factor for our ammonia and hydrogen. Well, it's a 2 for the ammonia and 3 moles for the hydrogen. So we look at here, 2 moles of ammonia to 3 moles of hydrogen. That is our mole-to-mole factor. As we continue, the relationship between our hydrogen and our nitrogen is 3 moles of hydrogen to 1 mole of nitrogen, which is what we had already done. And you'll notice here we have this answer, which is what we had already said. Okay, now, let's look at this one. Here's some more calculations with more mole factors. How many moles of iron 3 oxide can form from 6 moles of O2? Now then, we're going to use the concept of the relationship and do a problem. So, we are going to start out with 6 moles of O2. 6 moles of O2. Now, we have this relationship of O2 to Fe2O3. The relationship is 3 moles of O2 to 2 moles of Fe2O3. And so we have to figure out which one goes on the top and which one goes on the bottom. Well, if we're starting with 6 moles of O2, then we know that the relationship of moles of Fe2O3 to moles of oxygen has to have the moles of oxygen on the bottom, so this label moles of oxygen cancels out. Now again, where did I get this 3 and this 2? I got it from the balanced equation. The 2 goes in front of the Fe2O3 because the 2 is there, and our 3 is here for our moles of O2. So when you do the math, 6 times 2 divided by 3 equals 4 moles of Fe2O3. Now then, how many moles of iron are needed for the reaction of 12 moles of O2? Press pause and see if you can do this. Now, as we look at this problem, we need to know our iron. We are given that we have 12 moles of O2. Because this is a mole-to-mole ratio, our equation, our balanced equation is a mole-to-mole ratio, then we're going to use that mole-to-mole ratio in our equation. So we can choose, okay, we are going from iron and we're going from oxygen to iron. So here's our oxygen, the 3 moles of oxygen, and they're asking how many moles of iron do we need. So that's going to be 4 moles of Fe. So let's see, we have these different choices, 4 moles of Fe over 3 moles of O2, or 3 moles of O2 over 4 moles of Fe. Which one do we use? Well, we're going to start with 12 moles of O2, and then we're going to need to cancel out the label moles of O2, so that means our setup is 4 moles of iron over 3 moles of O2. The moles of O2 cancel out, so our label ends up being moles of Fe, which is what we needed. So 12 times 4 divided by 3 equals 16. Now then, our last problem, one more check. Using the following equation, how many moles of ammonia would we obtain from 4.8 moles of hydrogen? Press pause, see if you can figure out how to set this up. All right, Now remember that the coefficients in the balanced equation represent the mole-to-mole ratios. So we set up the conversion to cancel out the moles of hydrogen. Why? Because that's what's given. And then it's going to, whatever they're asking, that we need to go to ammonia, so that's the coefficient we use on top. So our moles of hydrogen cancel out. The only thing left we have is moles of ammonia. So 4.8 times 2 divided by 3. And our moles of hydrogen cancel out, our moles of ammonia is what's left. So 4.8 times 2 divided by 3 is 3.2 moles of ammonia.